Hello and welcome to the You've Got This Girl podcast, a space for celebrating all that we are as women, our struggles, our journeys, and our victories, sharing knowledge and inspiring stories of women accomplishing incredible things. I'm your host, Marilyn Brown, and my guest today is Dr. Tara Ruttley. Dr. Ruttley is currently the chief scientist for the Orbital Reef Project at Blue Origin. She also enjoyed a fascinating career at NASA in human exploration, where adaptability is everything. She holds degrees in biology, mechanical engineering, neuroscience, and anthropology archaeology. She has publications ranging from engineering to neuroscience and archaeology and holds a U.S. utility patent. She is also a keynote speaker who empowers others to better adapt to any situation by helping them understand how their brains process novelty. She teaches her audience about the biology of what happens to us in new situations and how intentionally seeking out novel situations will rewire our brains to embrace their biggest challenges. Welcome.
Thanks very much for the introduction. It's so cool to get to talk to you for a while.
I would love to hear about your early years and what inspired you to pursue a career in science and in space in particular.
All right. So I grew up a kid in southern Louisiana uh, to a single mom. I had a sister, and nobody knew anything about space at all down there, right? So it wasn't the thing, and so I though was a shuttle hugger. I grew up a kid in the 80s, and that was the space shuttle era. So I would watch the space shuttle launches regularly on routine on TV when they happened, and you'd see the big launches with the big flames and the fire and everybody launch on TV, and then most of the time people stopped paying attention after that. But there was something going on up there, and that were people doing experiments inside of the payload bay of the space shuttle. And so, these people, I would watch them on TV, and they would be spinning in chairs. They'd be wiring each other up. They'd be playing with flames and fluids and doing all these things. And they were the first ones to get to see some new kinds of behaviors and experiments that no one had ever seen on Earth. And so I knew I wanted to be an astronaut. And so I used to write letters to NASA. And back then we didn't have email, but I would write a letter, and NASA would send me back big envelopes full of pictures of astronauts and biographies of astronauts. And I knew by looking at it, I needed to either be a pilot or an engineer, and there were a very small number of actual scientists. So I decided I was going to go the science route, because when I was in high school, we dissected a cat and in biology class, I'm a cat lover. I have one sitting right back here. But what happened to me was I recognized that just looking at that thing in front of me was a machine that wasn't created by any human. It was created by nature, and it wasn't engineering that I was interested in. It was nature. It was life sciences. It was science. So that's what I decided to just go and pursue my bachelor's degree in biology at Colorado State University. And I was, as a biology student, I would come up with these really cool ideas. I would join all the space clubs, and I would come up with these cool ideas for what we could design and use in space as students. What did NASA need? Because the space station was being developed, and there was all kinds of needs. And so I was the only biologist always in these engineering clubs. And I came up with the design for an exercise machine to use in space. And I needed a group of engineers to help me build it and test it on the KC-135 airplane, which is something called the Vomit Comet, where you get 30 seconds of microgravity at the top of many parabolas over several hours. And so by kind of forming a team where I had a bunch of engineers surrounding me, I just got to understand what engineers needed and how I needed to communicate as a scientist to be able to bring to life as a team the ideas that I had in mind. So we had a great time doing that, and then I was wrapping up my bachelor's degree, and I was like gonna get my PhD in neuroscience, because that intrigued me in all my coursework that I took. I thought, the adaptations of humans and how humans think and behave, and what makes us do what we do, what makes us scared of what we're scared of. That always intrigued me. So I was going to do that, and the engineering students were like, no, you should take a minute. You should apply to just be an engineer. Apply to the mechanical engineering master's degree program at Colorado State University. And I was like, are you kidding me? I'm not going to be an engineer. I don't want to be an engineer. That's great. And they were, do it. So I did it. I applied. and I got in. So because I got accepted, I thought, well, maybe there's something to this. Maybe,
Mhm.
maybe the guys in charge of the mechanical engineering program think that I am capable of being an engineer and there's something to this. So, I went through my master's degree and I was actually the first one at Colorado State University to get the biomedical engineering certification
Wow.
back then. So that was cool. So I got to, emphasize biomedical engineering. And then I was going to graduate with that, and I was about to apply to a PhD in neuroscience. And NASA had a job fair, so I applied. I was like, "Oh, here's my resume," and they're like, "Well, thanks. We're having a job fair, even though we're in a hiring freeze, but we'll take your resume, and who knows."
Yeah.
And sure enough, 2 days later, they called me and said, "Hey, we have a critical hire need. We're opening up a new division in the engineering directorate, and this new division is called the Biomedical Systems Division.
Yeah.
And we need someone with your dual background to come and manage the exercise and medical equipment for the new
Mhm.
International Space Station." Because they said, you know, the way that we build hardware is that, the scientists and the flight doctors say, we need this hardware built to keep humans safe and alive and, this and that. And then the engineers will say, oh, really? Okay, here you go. And like they turn it into requirements, which could be expensive or hard on schedule. And so there's like some disconnect and some translation that the two needed to have. And they weren't
Mhm.
really, it wasn't coming across. So they saw me as the middle person to be able to communicate back and forth,
Yeah.
and help mediate these requirements and turn them into hardware. So I started out at NASA as an engineer,
Yeah.
even though that's not what I really had planned to go and do.
Yeah.
And so I started out on the exercise equipment, which was super fun, and what I knew about, and then after the first year, I transitioned into the medical hardware lead. And I will
Yeah.
say right now, that engineering degree has paid off my entire career. First of all, starting out in space in engineering, there's no better place to start. Quite honestly,
Mhm.
it is, especially when you're designing hardware for humans to live on the International Space Station
Yeah.
in space. You got to keep them safe. You got to keep it, reliable.
Mhm.
There's all these requirements and all these things to think about that scientists are kind of working in a gray zone and they don't think about those kinds of things. And so for the rest of my career, it made me realize that, humans are, again, I got to say, humans are adaptable, but they also have safety needs, and they also think and behave this way. And the engineering was just the perfect way to come into NASA and
Yeah.
get that done.
Yeah, I find it so fascinating, the concept of developing these tools for both medical and exercise equipment. And I was curious if you could share a little bit of the importance of the exercise regimen that the astronauts have while they're on the space station.
Yeah, so when you're in space or on the space station and you're in what's called low Earth orbit, you're really close to the Earth. You're about 250 miles up. It doesn't seem that far, but that big 9.81 meters per second squared gravity vector is down to the
Mhm.
microgravity level. So you're basically floating, so to speak. So there's no gravity force pulling on the muscles, pulling on the bones to make you have to walk anywhere or work against any forces or any loads. And our bodies are designed to move against loads of gravity. And that's why we have muscles to make us move, and that's why we have bones to hold us up. If you don't need to use those things, the body is really good at getting rid of what it doesn't need because it costs a lot of energy to keep things up. And if you're not using it, you lose it. That's just the body's way of being efficient. So in space, they're floating everywhere. They're not working that hard and they're at risk. And what happens if they don't do something about it is their bones start to atrophy or waste away, much like if you don't exercise for a while. And then their muscles do that, and then their bones will start to decompose a bit, or demineralize. So they basically become osteoporotic or osteopenic. They get
Yeah.
more brittle. So to counter that, the astronauts have to work out doing treadmill and resistive exercise and a cycle ergometer about 2.5 hours a day is what they're allocated. And we've been able to see over the last 25 years of the International Space Station is that when they do that, they're able to maintain that bone and muscle mass and that's really critical, and it's good for the heart too, because if you're thinking about, a 9-month mission to Mars, so, it takes 9 months to get to Mars and you're in a microgravity environment. Then you get to a Martian environment where there's 1/3 of the gravity of Earth. So you've got a gravity that you have to now get out of your vehicle and take that first step down that ladder. Um, then you want to be in the best shape that you possibly can. You don't want to have brittle bones. You don't want to have bad balance and fall down and hurt yourself or
Yeah.
break a hip or
Yeah.
what, right? You want to be strong. You want your heart to be strong. So
Yeah.
that's why we have the exercise equipment on the International Space Station for long
Yeah.
duration.
I would imagine too that there's a bit, with your neuroscience background, there's a bit of a neuroscientific component to it as well, as far as, at least I mean, I weightlift, I'm an athlete, and the oxytocin release when you're doing physical, workouts or physical exertion, I would imagine that there's a component of that as well for mental well-being.
Oh yeah, right. The psychological part. When
Mhm.
if you're a runner and you hit, if you're at a certain pace, it's kind of mesmerizing, it's kind of hypnotic, it's kind of meditative. And so yes, a lot of people find that working out is needed up there for their mental health. Not everybody likes to exercise, even in space though. So there are those astronauts who go are like, it's not my favorite thing to do, but you want that there for the
Yeah.
for familiarity as well, and for not just for physical health, but for mental health.
Yeah.
Yeah.
Yeah, and I remember talking to, because obviously you and I now know each other through Michelle, and during the episode that she had with me, she talked about the sort of like the schedule that the astronauts have and taking care of their mental health. And I know in your public speaking engagements, you talk about the biology of what happens to us in these new situations, and how if we seek out that novelty, we can kind of rewire our brains to embrace those challenges. Can you talk about some of the work that you guys do with the astronauts around that? Because obviously they're going to be in these novel situations. So how do you work with them to address the, complete
You know what?
novelty of the situation?
Yeah, so I'll tell you how this works with the astronauts. It's first of all through the selection process. Most of these
Mhm.
astronauts who are selected have a wide variety of what we call operational backgrounds. So they have been a pilot and a scuba diver and maybe a cave explorer or a mountain climber and an ice skater or a race car driver and a. And so these people are used to doing a lot of different things their whole lives, not just physical challenges, but mental challenges and environmental challenges. And the idea here is it's something called adaptive generalization, which means the more that you put yourself in those bigger challenging situations, the better you are able to adapt in the new environment. So by the time these astronauts have spent, they're pretty early or well into their careers, they've spent their lives doing all the many different things, that's recognizable in the selection process. NASA wants people who have a good operational background. So those people are more likely to apply, and they're more likely to get selected. And then once they're in, they get assigned to a mission after a lot of years of training, and they finally get assigned to a space station mission. They got about 18 months of training, and it could include everything from traveling around the world to learning new vehicle systems, to learning new languages. But also, there's some physical components in terms of preparing you physically, making sure your balance is in check, in order. And your balance is a big part of this adaptive generalization part, right? Because your balance system is the one where your eyes, your feet, your body part, your muscles, your inner ears all tell your brain that this is a new or an old environment. And for us as human beings, we're designed to recognize novelty. Like we don't like it necessarily because it's a lot of work, but our brains have been designed over the thousands and thousands of years to recognize novelty because it keeps us safe. If something is new and different, it gets our attention. So those are the kind of people. If you go with that, if you go with that idea, those are the kind of people that tend to apply to the astronaut program.
Yeah, I mean, it's so interesting when you mention the different, the eyes, the ears, all of the different senses. Like, right now I'm dealing with an ankle injury, and one of the things that I'm doing to recover is I have one of those balance pads, and one of the
Yes.
ways that we progress the rehab exercise is for me to balance on it with one foot with my eyes open, and then to close my eyes, and just like not
Yes.
having that feedback of my eyes throws me totally off, and I
That's
would
right.
imagine it's the same thing with microgravity, right? It's like your body, it's a totally different sensation. I would imagine that has to affect pretty much every system in your body when you have that
Yeah.
different sensory input.
Vision is our primary sensory input.
Mhm.
And so when you take that away, and in space, things are up or things are down. There is no up or down, right?
Yeah.
And so not only is your vision confused, but your feet aren't touching the ground, telling you that you're standing in this direction.
Yeah.
And the little stones inside your ear that usually gravitate down are now kind of floating around and not telling your brain it's telling your brain there I don't know where down is, and so
Oh,
and then you
interesting.
have like these sensors in your joints and in your muscles that
Yeah.
tell your brain where your body parts are, and
Yeah.
they're not usually where they are normally are anymore.
Yeah.
So it's quite a different array of sensory information, and they adapt on orbit. They end up adapting, which
Mhm.
is good. That's what you want, right? You want them to adapt to the new environment. The challenge becomes when they come back
Yeah.
and these systems are still adapted for space flight. Now they come back and their balance may not be right, and then that could be a risk issue for health. And so there's a bit of a recovery exercise and maybe a little bit of physical therapy when they come back, and just to make sure all their balance is in check and things like that. But for you, that ankle injury, once you injure your ankle, it's a highly proprioceptive joint, which means
Mhm.
a lot of information goes through that joint, and once you injure your ankle, you're more likely to injure yourself again in the future. So you want to keep that ankle really strong and rehabilitated.
Yeah. Yeah, I mean it's always so interesting to me because they always talk about when the astronauts when they come back and they're taller and
Yeah.
I and even the most recent case with Sunny, the two astronauts who just came back who were up there for so much longer than it was anticipated for them to be. Like I imagine it must have been interesting guiding through them through that when the initial, thought was they're going to be up there for a certain period of time.
Yeah, yeah, right. When you weren't prepared to be up there for,
Yeah.
9 months, you were only going to be up there for a few weeks.
Yeah.
But luckily, those two are super experienced. And so, it might have been different had it been a rookie. Who knows, right, man? And of course, everybody else is different. But the one also another interesting thing is once you have flown once, your symptoms aren't as severe if you fly again and again and again.
Interesting.
So it gets a little easier with each reflight. Yep.
Very interesting. And so you meant
Adaptive generalization,
yeah,
adapting.
yeah. And so you mentioned that after getting your PhD, you transitioned more into the scientific experiments. And, talking to Michelle, obviously, when she sends her students' experiments up there, it's a really cool experience for them. Can you discuss a little bit what the importance of conducting those experiments in microgravity?
Yeah, sure. So I did finally obtain my PhD in neuroscience while I was an engineer, and I decided, okay, now it's time to go do something in science. And so I applied to be the associate chief scientist for the International Space Station and was selected. And when I got in there, it was our job to basically we were a tiny little office of science nerds in a big engineering organization. And it was our job to protect the science to be done on the International Space Station. So the International Space Station is an orbiting laboratory where astronauts live and work, and the primary job is that they do science experiments. And they do it because it's the only place in the world that we can do experiments in a sustained environment where there's no large gravity vector. So when you take that large gravity vector away, that big force of gravity, things change. Behavior of processes that we know it change. It's not very intuitive. So, for example, let's see, sedimentation. If you have a bottle of cough syrup in your cabinet, all the good stuff particles will settle to the bottom, and you shake it up. You have to shake it up if you want the good stuff when you take it. But in space, if you shook it up, the particles will stay suspended, and that's neat and all. But what happens is scientists can study the natural interaction of those particles and how they would naturally behave with each other, and possibly take that information and make an improved form of cough syrup. And so it applies to things like how fluids behave. Fluids without that force of gravity, capillary action takes over, and water will climb the walls or hide in the cracks and crevices and kind of climb up out of the cup, maybe, and up your arm. And, water behaves in a way that we don't expect it to here on Earth. And even flames and living organisms, and even new technology that you think might work the same in space on Earth. Sometimes it doesn't. So that is the environment that is the International Space Station. And that is why it's a world-class laboratory. They're doing experiments across all disciplines for two reasons. One is for all the benefits that we bring back to Earth. And that includes studying the human body too. And that bone loss that we talked about and the advancements that we've made apply to osteoporotic patients here on Earth as well. So it's to bring benefits back to us here on Earth, in addition to making sure we understand how our astronauts can live and work in space for exploration purposes for longer periods of time. So the laboratory is always busy. There's always about 6 people up there at one time. They'll stay from 6 months to up to a year and doing lots and lots of science. And over the last 25 years of space station research, we've had some really cool benefits that come out of it. And then there's more to come. Now, it is expected to retire in the year 2030, but NASA is working on a way to build the next space station through financing commercial companies to try to do that.
Right.
See,
Yeah.
2.0.
Yeah, I worked for Orbital ATK, and so that's actually how I know Michelle. And so, I remember all of the different Cygnus missions that we had going back and forth to the space station, presumably bringing them materials for science and bringing back things that
That's
they
right.
were
Science,
sending
science,
back.
science.
Yeah,
Yes, very good.
yeah, we had. I remember at the time they were talking a lot about the habitats or the what you're discussing, the replacement for the space station.
Yep.
Out of curiosity, like what is, do you know, like what is the plan for, would it be sort of jettisoned out, or like how would it deorbit safely?
Yeah. So NASA has funded SpaceX to come up with a deorbit vehicle that basically attaches to the International Space Station, and over about a year and a half's time, it slowly drags the station down. And so the closer to Earth it'll get, the drag will cause it to slowly and controlled manner re-enter the Earth's atmosphere and burn up. And any of the pieces that don't that survive the burnup of the atmosphere will be pretty much tanked into the Pacific Ocean, where there's no people.
That's so interesting. And so
Yeah.
then that's fascinating. And so is there any sort of like recovery effort to kind of keep some of the sort of historical significance of it without having it to kind of burn up in the
We've
atmosphere?
so like we've so thought so many ways about this to try to. The thing about the space station is it was built with the space shuttle. So
Mhm.
many of the parts have to fit inside of a space shuttle payload bay, and we don't have a capability for that anymore. Every capsule that we send up can only bring a certain amount of things back, right? Like,
Yeah.
so we can't fit any of that stuff. And even if we could, it'd be expensive. It would be, you have to ask yourself, what's the best use of taxpayers' dollars on
Right.
this? If there's any small items that we can bring back, surely for the museums and for the public to see, surely NASA will do that. But it's
Yeah.
a balance of, what makes sense technically and financially.
That makes sense. So what are, I guess, if I can put you on the spot a little bit, what are some of the advancements that have come out of the science that has happened on the space station that you find, most remarkable or that stick out to you the most throughout your career?
Yeah, I think what's really cool. I mean, there's a lot of examples that we talk about. I think if you I'm trying to think of one that's really cool, but that you might be familiar with it. So, for example, Merck Laboratories, they make the drug Keytruda. It's a cancer treatment drug. I know someone who's taken Keytruda, and when you take that drug, you as a patient, you have to go in and get it administered intravenously, and you have to sit there and wait for the
Mhm.
drug treatment. And Merck was interested in trying to improve that in two ways. One, to improve shelf life. That's always a thing we want to do on Earth, and to improve the way that patients could take that medicine. Maybe they didn't have to come in. Maybe they could get their own shot. Maybe it could be an oral medicine. And so what they did was they sent up their Keytruda solution and tried to grow up crystals of the medication. And the reason we try to grow up crystals in space is because of the lack of sedimentation and because of the lack of convection. You can grow up really nice crystals, structures of a protein or a medicine or you name it, and then you can get it back to Earth and you can look at it really closely and kind of try to find places you hadn't seen before. And sometimes you find places you hadn't seen before, or you get sizes that you've not seen on Earth, and it tells you more about that particular molecule or that drug you're looking at. And then you can take that information and improve on it. So that's what Merck did. And that's in process right now for Keytruda. But our Japanese colleagues have done the same thing with a protein and its medicine that tries to prevent the progression of Duchenne muscular dystrophy, which is a muscle wasting disease. They did the same thing with that crystallization a few years ago, and actually made it through clinical trials. I think it's actually out and in improved medicine now and is being used in the population. So, there's lots out there about water improvement technologies and material improvements and even improvements in making like optical fibers for communications and the promise of tissue production and mass stem cell production. There's all these interesting results that have come from space station, and now the next step is to scale that. How do you scale that so that it reaches people around the world, and it becomes one step past an experiment with some interesting results to application, like these few examples.
Yeah, and then I would imagine too, like there's got to be different things that come out of it as far as, from like a botany perspective, like when you think about growing plants in space
Yeah.
and the implications of that, or even you were talking about, lower gravities like on Mars, you know, how do these plants grow in space, and how does that affect how we would sustain ourselves, our traditional agricultural methods?
For sure, even watering, because right in space, like I said, water behaves differently. So how do you water those plants? And as it turns out, it's very difficult. And what we've learned from watering the plants on station is to do with roots and root aeration, and has been able to tell us, how we could apply that kind of watering capability, or our knowledge gained from how roots take up water, to the larger agricultural systems here on Earth. And that's just one example of plants, but we've seen how we've been able to parse out light versus gravity effects on growth of the plants. And interestingly, there are some really cool scientists who are well known in the community who were able to sprout model seedlings from Apollo regolith samples taken from the Apollo missions. They grew them up in Apollo regolith here on Earth and were able to sprout them, which was fascinating to me from an exploration standpoint, because everybody wants to know, can you grow plants on the moon? Like, can you stick a seed in there, water it and grow it?
Yeah.
Well, on Earth, they were able to do that. They provided a little bit of nutrition, but the plants, they grew, and they were somewhat stressed out, but they sprouted, which was the first time ever we've grown anything in a regolith. And that was collected back in the Apollo missions.
That's amazing.
Yeah, it was cool.
Very cool. Well, I am also interested in asking you, to the extent that you can talk about it, because you work for Blue Origin now on the Orbital Reef project. Is there anything you can share about, what that project is and what your work is there?
Yeah, so Orbital Reef is Blue Origin's commercial space station that's currently under development. It's being funded by NASA through its preliminary design review, along with a couple of other competitors NASA's funding. So we're all working through this period right now to design for NASA and for the world a commercial space station, a first ever commercial space station. So with our primary customer planning to be NASA, though, we want to open it up to the rest of the world for commercial use and be able to scale those results that I talked about that came from ISS, to give access to scientists like you and me who may want to fly with our own science. We can't do that exactly on the International Space Station, and just open it up to people who've not been able to experience low Earth orbit before. Whatever your plans are for using low Earth orbit, whether it's visiting temporarily, whether it's doing science, whether it's manufacturing. And so that is our version of the replacement for the International Space Station, and that's what we're working on today. And so my job on a daily basis is to work with the engineers. As chief scientist, I work with the engineers to design the laboratory on our orbital reef, on our space station that meets the needs of NASA and commercial businesses who may want to use it. So it's from around the world. So we have a wide range of capabilities that we're designing for. and to meet a wide range of needs. And it's been really super fun because it's kind of like going like when I joined NASA in 2001, we had just sent the first astronauts to the International Space Station 3 months
Yeah.
before that.
Wow.
The thing was already designed and built and started being built. And so that was already done. I showed up and just helped it along, right? Like now I'm like it's like getting to go back to the beginning of my career, but with a lot more knowledge and
Yeah.
experience to kind of get to start a space station from scratch. So it's been pretty fun. It's been pretty cool.
That's awesome. Yeah, so it's interesting to me because, having worked at Orbital within the aerospace industry, I always found it interesting because in my mind I felt like there was I assumed that there would be a lot more tight regulation around like launches and the what can be in space, like responsible deorbiting, all of these things. And like I was kind of surprised to find that like internationally the regulation is not really there. And I feel like even more so once it becomes more of a commercial endeavor where lay people like you or I would be involved in like, being in space. I'm curious to see where that goes as far as like space debris and things like that and responsible use of space is concerned.
Yeah, that's a really good question, and it'll keep people busy for a long time. Policy and regulation. There's a lot to do because I think the technology and the technology and the science advancements are and the promise are way out in front.
Hmm.
And yeah, what's still got to come is regulation. So whichever space station NASA selects to go forward, or however many commercial space stations will go forward with or without NASA, will have to meet these these regulatory environment and restrictions. And so I said this even when I was at NASA before I came to Blue, which was 3 years ago. I said, wow, these regulations they're going to make or break the industry, right? Like, so there are smart people who know that this will make or break the industry. So they're looking at, so there is a moratorium on the FAA requirements for commercial space flights and participants that have been extended, to give an opportunity to those private commercial spaceflight companies like Blue Origin to demonstrate the safety and viability of this industry without
Right.
yet being hindered by regulation. So that is, for example, our new Shepard rocket that we show that we can safely launch people and payloads to space over and over again, and that we can meet all these other environmental regulations and things. So there is a time period that we're in right now where the regulatory environment is allowing commercial to do what we need to do safely and under certain requirements and such. But it will grow. I mean, and think about it. Things like, there's talk about, oh, you could make a tissue, a heart tissue on the internet on your new space station, and because it grows so well in gravity and microgravity, and then send it back to Earth and put it in a human. And if you think about anything that you create in space that needs to go inside of a human, anything you create on Earth that goes inside of a human goes through processes after process of certification and requirements from the FDA. I mean, these FDA inspectors show up in your lab and make sure that your lab equipment is in check and is clean and is meeting the standards, right? So how does the FDA regulate something like that in
Yeah.
space? So
Well, let
that's
alone
never
trying to
been done.
have a human heart re-enter in.
There's so many like things left to think about and talk about because the science, we know it's possible. We know it's possible, but there is so much work left to be done on all the in between.
Yeah.
And that'll keep people busy for a long time.
Yeah. And so another thing I wanted to ask you too is, obviously coming back to the core of the podcast, which is about just women being women and rock stars. What advice would you have for any young women out there who are trying to break into the sciences or interested in sort of that kind of career path?
I would say, gosh, always be prepared for anything. Like I said, with my engineering degree, it's just one example of many, but there's just not enough time on this podcast to say that the opportunities that showed up to me that I didn't think I wanted, but other people thought was a good idea. Like it's kind of a good thing I relied on them because if it were up to me, I probably would have ignored it and missed out on some really great opportunities. So if you want to get into this area, by all means, you reach out to anyone you know in the area, you go to the conferences, you write the letters, you write the emails. People inside of the space industry generally want to help you join. It's a small family, and they're generally just want to be helpful. But if someone calls you and says, "Yeah, you can come to work for us as an internship, and you'll be working safety, or you'll be working no, you'll be working science communication," and you're like, "But I'm an engineer." Do it. Take it anyway. You might enjoy it. You might like it, and you're going to be able to show them what you're capable of. And the one thing that anybody needs the most in this industry is flexibility and the ability to just do the stuff that's hard and not run from the stuff that's hard. If someone gives you, an assignment you don't think is for you, you just step up and do it because it's all hands on deck, and that also makes you just adaptive, a better adapter.
Yeah. Yeah, I remember Michelle talking about that with Nemo Aquarius. Is like, she ended up in that project sort of just, it was something that nobody wanted to kind of do. And then she ended up being able to go scuba dive down and help astronauts train. I was like, I mean, it's the perfect
Yeah.
example of like, nothing ventured, nothing gained kind of thing.
That's right. And that's how I met Michelle in
Right.
is in Nemo when she was training me as an aquanaut. And we've been friends for the last 20 years now. And, not just friends, but colleagues in the business. So
Yeah.
you never know who you're going to meet.
Yeah. I imagine, I was telling her too, like, I imagine that must be so interesting, like being in that environment. I mean, obviously as she mentioned, it's a wonderful analog for space, but man, I
Oh,
mean,
yeah. High pressure. Interesting is a good way to put it. I
yeah,
was like, I was the only female. I was the youngest. I was the only non-astronaut, and it was my mission. I was leading, in terms of the engineering and things. So it was a great lesson for me on
yeah,
again how to design experiments and engineering hardware for the astronauts in a real mission environment.
yeah. Yeah, I mean, it's something that I do miss about the aerospace industry. Because I was in more of a communications role, like a marketing role. But gosh, some of the most just passionate and talented people I have ever met and had the
Yeah.
joy of working with. Like, they would be sitting there. It would be after a meeting, and I have kind of an innate curiosity. Like I was the person where, I didn't just want to be the person at the conference booth that just took somebody's card. Like I wanted to be able to have a decent conversation with people back and forth to a degree. I don't have, a degree in mechanical engineering or anything like that, but be able to at least answer a few questions intelligently. And so I would sit there after meetings with some of these folks, some of our engineers, and just have them break it down for me,
Yes.
and like they'd be sitting there diagramming out and orbit, and this is how it stays, and this is how you get your direct TV. And I loved it. Like it just,
Exactly.
they would sit there for a half hour with me and explain it, and you could just tell they were so passionate about what they
That's right.
do.
And that's one of the cool things about being a science communicator, because it's your job to ask all those questions. You get to talk to them all, and they get to explain all that to you. It was a fun part about my job in the International Space Station too, because I had to do the same thing, right? I had to like go on camera and explain the science that we were doing on space station. Some of this I may not have known a thing about. I had to go like you and
Mhm.
make phone calls to some of the scientists that had experiments, like explain
Mhm.
this to me like I'm a eighth grader, right?
Yeah.
Like this is not my area, but like you said, it's so cool to be able to just hear about all the passion from all
Yeah.
the different scientists and
Yeah.
engineers that do this stuff.
But it's cool too because it's really it's a skill to be able to take those things that are these really intense and technical concepts and be able to break them down for the layperson. Because not, I mean, I know some really
Yeah,
smart people that can't do that. It's not everybody that can take
that's
something
right.
that's at that level and then just make it digestible for somebody who doesn't have 10 years of schooling in that discipline.
Exactly. Yeah. Yeah. It's not for everybody. Not everybody wants to do it. And it's a lot of responsibility too, because you are representing a scientist, and you don't want to, you know, minimize it down so much that it makes it look like you're neglecting their important work, right?
Right.
But there is a level where you have to be able to communicate it to
Yeah.
the public, and the public doesn't necessarily want to know all the details.
But it's also so, I feel like so important to the future survival of science and
Oh
of
yeah.
these disciplines because in order to get somebody interested enough for them to feel like this could be me, I can do this, you have to make it accessible enough that people can get excited and get interested and feel like they might
So
have a
true.
place there.
So true. And not only that, not only do you belong there, but that if you can communicate any work that you're doing, you're gonna be more than likely to be able to keep the funding for that kind of
Yes.
work. So that's what I was doing for Space Station, is justifying its existence. And that's why science communicators are there, to inspire, to justify, to explain, and to educate. And I think inspire is, like you said, inspire is probably number one.
Amazing. Well, I wanted to
So
thank you
fun.
so much for your time today, and I'm excited to see, where your current projects go, and to keep in touch to be able to learn more about the amazing work that you're doing.
Yeah, so fun. I guess we'll know in the next few years what becomes of Orbital Reef, and all the fun that's ahead for science in low Earth orbit. It's not going anywhere. The space station's retiring, but the United States wants to keep that really great capability. So here's to the future of low Earth orbit research.
Awesome. Thank you. Well, thank you for your time.
Yeah. Thanks.